congratulate you on being quite so numerous at this hour of the morning on the final day. We have two sessions. In this session, we'll move to chapter 11. So we'll follow the plan that we made, and we'll look at chapter 11. Then, after the coffee break, we'll come back to the ideas that Rüdiger was explaining at the end of yesterday. They belong partly in chapter 10, these reduced form models, and then they will be further used in looking at counterparty credit risk, a little bit of chapter 17. So to talk about portfolios, yesterday in credit risk, it was really only about the default of a single firm, whether we look at it in a structural model, a firm value model, or a reduced form model. And I want to take you back to one picture I made, this one here. This picture explains the Mertens model. Each path is supposed to represent the evolution of the value of the assets of a company. It's the asset value. How's that? Is it okay? The evolution of the asset value. And at 1 year, there is debt to be repaid. And in Mertens' model, this is the only time debt is repaid. It's a one-period model. And whether or not you can repay that debt depends on whether the path ends up above this point here. So if the path ends up down here, you default. If the path ends up here, you don't default. But of course, if the path ends up here, this is a pretty good outcome. The company is doing well. Maybe the company should be upgraded. But let's say that this is a B-rated firm. Maybe if the path ends up here, it should go up to A-rated or double A-rated up here. Maybe it could even be upgraded to triple A. So depending on where you end up here, you may default, or you may have a downgrade. Your rating may stay the same, or you may have an upgrade. So this is the idea that I'm going to develop in this chapter. However, we will add a dimension. We're going to look at portfolios. That's the key idea. We look at portfolios. And so this extends chapter 10, but it also relates to chapter 6. It is about multivariate modeling, except the outcomes are discrete. Mostly, in fact, 99% of the time, there are only two outcomes, default or non-default. We can't, at various points, we think of other outcomes like downgrade, upgrade. But largely, we'll just think of Bernoulli models, default or non-default. And there will be two modeling philosophies, threshold models, which will relate to Copulas. So Copulas will make a reappearance, and mixture models. But in fact, then they will be seen to be much the same thing, two views of the same thing. The mixture models have some computational advantages. I'll run an R script to suggest why that is the case. And then finally, having talked rather abstractly about portfolio models, we will think about how they are calibrated or estimated. So why is this chapter really important? Well, credit risks are dependent. Defaults are dependent. Downgrades and upgrades are dependent for rather obvious reasons. On the other hand, because of common factors in the economy, economic reasons. So if we're in recession, so GDP is not growing, or unemployment is growing, whatever, there are common factors affecting all firms, and so there are likely to be more downgrades, more defaults. So there's dependence caused by economic factors. There are also more direct dependencies. If you have two firms and they have close business relationships, perhaps one is a supplier of the other, perhaps B is a supplier of A, and therefore the default of company A may have a direct impact on the default probability of company B. So these direct business relations, this is often called contagion. So you catch default from another firm, and this one here we will call common economic factor dependence. So it seems reasonable to think that there will be dependencies. Firms will not default entirely independently. And why is this important? Well, if you only retain one idea from this chapter, it should be the idea behind this picture here. And so this is a fictitious situation. We have a portfolio of 1,000 credit risks, and you can think of them as loans, all for the same amount. And we will assume that the default probabilities are all the same. So the default probabilities for each of these loans are 1%. And we draw two models. First of all, case one, which is the red case. This is independence. If all of these firms default independently, you have the loss will effectively be a sum of independent Bernoulli indicators. And so it will be a binomial distribution. And a binomial distribution is well approximated by a normal distribution. So you see pretty much a bell curve here, a red bell curve. On the other hand, oh, yeah, the mean is, why is the mean at 10? 1,000 loans, 1% default probability. The expected loss is 1% times 1,000, so it's 10. An important point, because what we now do, we consider the black line, we do not change the default probability. So the default probability is still 1%, and that means that the expected loss will still be 1%, but we add a small amount of dependence. So in fact, the amount of dependence we add is a default correlation. Well, I'll say exactly what a default correlation is. Well, I'll say it right now. The default correlation is the correlation between two Bernoulli events. The event that company I defaults and the event that company J defaults. And we add what appears to be a very small number. This is not 50%, this is 0.5%. So, yeah. So when you look at this, 0.5%, a correlation of 0.005, it appears to be almost nothing. And this goes back to a point that Paul made, this idea that if a correlation is nearly zero, that means effectively independence. Well, it doesn't. In fact, this level of default correlation leads to quite profound dependence. So what happens to the distribution? The mean is still at 10. The mode shifts to the left, and we get a long right tail. We also get some probability mass here. And so you can immediately think about, well, what does this do to a percentile? Suppose that we determine capital at the, let's just say the 99% percentile. For the red curve, that might be somewhere here. So the 99th percentile might be somewhere here. It might be about 20, but for the black curve, it could be about 40. It could be about double the amount. So adding a little bit of correlation gives you a tail and has huge implications for the amount of capital you should hold against defaults in this portfolio. Now, this picture is also relevant to the story of CDOs that we don't tell in this particular course. But in CDOs, of course, they were divided into tranches according to the number of defaults in the portfolio. So you might have an equity tranche if there were some defaults, and then you would have a middle tranche if there were more defaults, and then if there were a lot of defaults, you had a senior tranche. And if you imagine, and perhaps we imagine that the equity tranche is down here, ending about here, and the middle tranche, mezzanine tranche, goes up to about 20, and the senior tranche starts at 20. Well, in the red curve, you very seldom get losses in the senior tranche, and not so much in the equity tranche as well. But as soon as you add the dependence, you widen this distribution, and you start to see defaults in the senior tranche. You also see more defaults in the equity tranche. So this picture also has relevance in the story of CDOs, but we, as I said, we didn't plan to tell that story this week. Yeah. The black one, what it is a Bernoulli mixture model where the conditional default probability of all the firms has a beta distribution. It's sort of the simplest dependent Bernoulli model.
It's used in practice. It's
Yeah.
a standard model.
Yeah, it's...
See it later on. Alex will explain the underlying model that is used to draw the
Effectively. Yeah, effectively. You'll see a model that's very similar, not quite identical, but in fact, all of these mixture models would behave qualitatively the same way. There's nothing special about the model or odd about the model. So the lesson that you draw from this picture is true for any credit risk model that is used in practice.
Can I just one little comment?
Yeah, a comment here and a question there. Question first. Yeah.
How would you normally model the common factors? I mean, I can understand that the direct relationship can be modeled with the correlation factors, specific wine chains. And how would you do the common?
Well, we're going to go back to the factor modeling philosophy of Chapter 6, and we're going to assume that there are factors out there that perhaps affect industries. In fact, that's exactly what I'll do at the end. We'll do an industry factor model. We'll say that the dependencies come through the broader economy and that companies in the same industry are most correlated in terms of their credit risk.
It's a similar idea as we used sort of in a one-firm case yesterday. You make the default probabilities random. You can think about it as so they are random, and then given the realization of the default probabilities, these firms will default independently. If you want an economic interpretation, you could say, well, in one scenario where the default probability for all firms is high, that's like a recession. The other one, when it's low relative to its mean, that's like next year is going to be surprisingly good. And that is what creates the dependence in this model. And you can view the default probability as a common factor. If you want it a little bit more complicated, you write the default probability as a function of some fundamental economic factors. That's the structure of these models. The issue remains now how to estimate, of course, such things. But,
so we'll try and answer your question by even doing an example if we get there. Paul, you're happy. So remember this picture. Is this very little dependence? Well, clearly not. If this amount of correlation can change the distribution in that way, then it's not a small amount of dependence. And our intuition about correlation values breaks down when we look at rare events. Default is a relatively rare event, 1%, and a correlation of 0.05 between two Bernoulli events is not nearly independent. Did you want to say something?
Yeah, I also want to say something.
Yeah.
Because, well, I think, if you bring that picture back once again, if you're tired and you're already filled up, then the one thing you should remember from this morning is probably this picture.
Yeah.
What we learned from this picture is the amount of dependence default correlation as one way of measuring it crucially determines the tail of the loss distribution. Of course, also the quality of the firms in the portfolio will affect it, but that's what you would think. Immediately, the dependence comes more surprising. Now, if you relate that to the subprime crisis in the United States, that's exactly what the models got wrong. What was happening was that for the first time, house prices throughout the United States were falling. In the past, it seems that they were maybe falling in California, but then rising in New York, or the other way around. But this time they were falling throughout the country. At the same time, interest rates were rising throughout the country, which meant that unusually many of these very shaky mortgages defaulted, which meant that there were unusually many defaults. So what firms got wrong in their valuation models was the amount of correlation between defaults. They had, very loosely speaking, they used the too low value of rho, and they did many other things which were wrong, but one of the things was that they used the too low value of rho. Of course, they were also not really most users of these, or buyers of these CDOs or asset-backed securities were also not even aware that essentially what they did was speculate on default correlation. But that's what you do when you buy a senior tranche, for instance, of an ABS, and they speculated wrong. They underestimated the amount of dependence that was there, and the result we will see.
In credit risk, a lot of effort goes into determining the default risk of a single obligor, but actually that's not so important. I could take this example and I could randomly double or triple or quadruple some of the default probabilities, maybe reduce others. I could play around with these numbers. The picture would hardly alter. The important thing is the default correlation, which is what Rüdiger is saying. So all the effort that goes into scoring and measuring the risk of an individual in a portfolio, it's not unimportant, but it's also important, but it's actually second order to modeling the dependence.
Essentially, it just shifts the distribution there. Whereas the other one changes its name.
I have a feeling we're going to talk about this picture for. Do you want to talk?
Just an exercise for the students is make them perfectly dependent. They're all the same. How does the picture look like? They're all the same. Yeah, absolutely. You have 99% peak in 0, nothing happens, and you have a huge loss of 1,000 way out. So this shifting tail up, mode left, you can nicely see that the extreme case, perfect dependence, is this singular peak in 0, the mode to the left, and the tail very out. Now we stop on the picture.
Now we start with the pictures to make some kind of progress through the modeling. Okay, so there will be M firms. No, we need to go on. Come on. There are M firms, and the time horizon is 1 year. We're only going to really worry about default and non-default. In the book, you'll see that we look at the slightly more general situation where you have a rating indicator, RI, which may take n+1 values. So 0 would be default, and then 1 would be the lowest rating, n would be the highest rating. At time t, small t equals 0, all the companies are in a non-default state. So if you see a Y, it's a default indicator. If you see an R, it's a rating indicator. And so Y is 0, no default. Y is 1 means default. So we can, if we look at a single period, let's say 1 year, we can describe the pattern of defaults and non-defaults in the portfolio by a random vector Y. Okay, so it's some sort of multivariate Bernoulli. So Bernoulli is the name attached to the 0-1 distribution, the special case of binomial. I suppose a good name in Switzerland. And so really, this chapter is really about multivariate Bernoulli distributions. Just a little bit more notation. How do we describe the distribution of a random vector? This goes back to chapter 6. We could write down the distribution function, or we could write down the joint probability mass function, the sort of density in this case, and this would be the probability of a particular pattern of 0s and 1s. So this might be a 0, that means company 1 doesn't default. This might be a 1, so company M defaults. And so we describe particular patterns of default and non-default by the probability mass function. And then for any individual firm, the default probability is PI. So that's the basic notation. What about this default correlation? It's simply the correlation between two Bernoullis. So that's the formula, 66, the formula for default correlation. It's a covariance divided by the product of standard deviations. So there are a few little sums here, which the first time you see them, you have to check all the details, but how to calculate the variance of a Bernoulli random variable. And so once we've done that, we have the correlation formula. Sometimes we will use a random variable to denote the total number of defaults in the portfolio. So often we use a capital M. So small m is the portfolio size. Large M is the number of defaults. If a firm defaults, we probably wouldn't lose our entire exposure. So we've lent, the exposure is whatever, EI, some number here, that represents the amount of the exposure. If you think of the loans, that's the amount that's been lent. If you think of bonds, this exposure will be partly the principal that you're expecting back and will also reflect the interest payments that you're counting on getting. So depending on the product, the exposures may be more or less difficult to calculate. Easy for loans, pretty easy for bonds. In counterparty credit risk, the whole business of working out what the exposure is very difficult. and will also depend on the timing of default. But let's assume for our purposes that EI is not a problem. We can work out our exposure. Delta I is the fraction of that exposure that we will lose, the so-called loss given default. We may lose 60% of the exposure. So delta I is a number less than or equal to 1. So how do we determine the portfolio loss? Well, we add everything up. Over the portfolio, we add up the exposures times the default indicators, which are either 0 or 1, times the losses given default. So in this chapter, this is really the key object. What is the loss distribution? I mean, these are pictures of loss distributions in a very simple model where all the exposures are equal, where losses given default are 100%. So in this chapter, it's about the portfolio loss. And where the dependencies we will concentrate on are the dependencies in the vector y. The other things could be dependent as well, in particular the losses given default. In a recession, it is quite likely that we have correlated losses given default. Well, it's quite likely that they're correlated in general. In a recession, you recover less in bankruptcy proceedings, and so the losses given default are more, and perhaps in a good period, the losses given default are smaller. But we neglect those dependencies, and as I've said, we'll just concentrate on the dependencies in the vector y. Now, in credit risk, quite often you have a couple of models that look different, but actually end up being the same model. And so we have a notion in the book of models equivalent. Two credit risk models that might look a little bit different, if they lead to the same multivariate distribution of the default vector, we say they're equivalent. I think that's probably enough from that slide. So the first modeling, the first style of modeling, threshold models, this is where the Copulas come in. So you'll see we'll have two sections. We'll have a section on threshold models and then later a section on Bernoulli mixture models. Both of these sections begin with abstract definitions, but the ideas behind these definitions are really straightforward. The idea is that in a threshold model is really in the picture that we looked at before. In a threshold model, the idea is really in this picture. You have to think of a series of thresholds. You have a threshold here for default. You may have other thresholds for different rating levels. So you simply think of a series of thresholds plotted on this line here. And that's going to determine whether a company defaults or not. So for each company, there will be a critical variable X. In the Merton model, that critical variable is the value of the assets at time t equals 1, or the log value of the assets at time t equals 1. If we want something normally distributed, we could take the log value of the assets. And so think of these X's as being value of the assets at the time horizon. So these X's are in general going to have continuous distributions. But in order to make defaults and rating migrations dependent, we are going to put the dependencies into this vector. So this is going to be a vector of correlated critical variables. So we have one for every firm. And then we have a matrix of thresholds. We have a matrix of thresholds. The number of rows is the number of firms, and the number of columns represents the number of states that interest us. Are we interested in rating categories and default, or are we only interested in default? If we're only interested in default, then n equals 1. And the model simply says that if the critical variable lies between two thresholds, then the state variable is set to a particular level. So let's say the state variable is set to j if and only if the critical variable lies between these two levels. In a default-only model, we can put yi here. So we will have yi is 0, provided the xi is above a threshold, and we will have yi as 1 if xi is below that threshold. So the x's are the critical variables, and you can think of this asset value Merton interpretation. Default occurs if xi is below let's say in this notation here, if xi is below di1, so we can immediately write down what is the default probability. The default probability is the probability, f is the distribution of xi, of being below the lowest of these thresholds. Okay. So how do we describe one of these models? Perhaps just to go back to that. The model is fully described by x, the random vector and its distribution, and d, the matrix of thresholds. This part has all the randomness. This is just a series of levels. In a default-only model, then this d is just a vector. So we have two vectors, something random, something deterministic. We can make some calculations in this model that are pretty straightforward, but we're going to get down to the word copula. Why are copulas in these models? So, firstly, there are a couple of notions of correlation in a threshold model. There is default correlation, which is the correlation of these yi's, the indicator variables. And then we can also talk about the correlation of the x's. And the correlation of the x's is usually called asset correlation because of the Merton interpretation. Because of Merton's influential work, regardless of what these x's are, and they could be something other than, strictly speaking, asset values at time t equals 1. Regardless of that, we tend to call these correlations of the x's asset correlations. So these are different. The default correlation and the asset correlations are not the same number, but they're going to be related. They're going to be related through the copula of the x's. So, and how exactly? So to compute the default correlation, you're going to need the covariance of the y's. So you're going to need the expectation of the product. And what is the expectation of the product here? Well, this is only 1 if they both default. This product is either 1 or 0. And this product is only 1 if they both default. When does that happen? Well, the first company, the critical variable ends up below the threshold. And the second company, the critical variable ends up below the threshold. So we have a joint probability here. And we apply the result that Marius explained yesterday and Rüdiger the day before, and actually on Tuesday, and which therefore is now very fixed in your minds, Sklar's theorem. And we see that, and we know that we can write this as a copula evaluated in the marginal probabilities. A copula evaluated in the marginal probabilities of default. Now, I haven't said what distribution X has, but in many models in practice, X is assumed to be multivariate normal. And therefore, in this expression here, you get the Gauss copula. You get the Gauss copula. If X is multivariate normal, as in many models in practice, the correlation of Xi and Xj determines the copula of their joint distribution and hence the default correlation. So you may immediately be worried by this idea that we're going to take normal. That may worry, it should worry you. There should be a big question mark if X is multivariate normal, because we spend a lot of time criticizing the multivariate normal. Now, the standard industry models do assume normal because the Merton model is based on geometric Brownian motion. You have log normal distributions. The log is not important. By taking transformations, we turn that into a normal distribution. So if you do a Merton model, you automatically get normal, multivariate normal distributions. If we do a multivariate normal Merton model, that is for every firm, we have a correlated geometric Brownian motion, then we're going to get a multivariate normal distribution. Is that a big problem? Maybe we should have a model where the x's are multivariate student, and we could do. And there's a lot of papers, including contributions by Rüdiger and myself, where we look at alternative distributions for x. And this is quite important. There will be differences in the properties of these credit risk models and in the tails of these loss distributions according to the copulas we choose. However, I will say that if we calibrate models to have very similar moments, the actual choice of copula, although important, is not so critical. It's not so critical. If the models are calibrated to the same information, there will be differences if there are models with different copulas, but not necessarily very profound differences. If you want to look into that more, in Chapter 11 in the book, we have a lot of model risk experiments where we look at changing the copula in a credit risk model. For my purposes today, I will actually stay with the Gaussian copula models. And not that that should worry you. These models are reasonable if calibrated well. They're not necessarily the most conservative. But for expositional purposes, I'll actually stay with the Merton model. If two threshold models, if we have two threshold models, so we could set up two different threshold models with different x's, with different threshold values. If they lead to the same default probabilities or transition probabilities, and if the critical variables have the same copula, then they're going to be effectively the same thing. They're going to lead to the same loss distribution. So in fact, the question of whether two threshold models are equivalent or not basically boils down to, do they share the same copula for the critical variables?
But when you say two threshold models, that's with different b's?
Yeah, so, or different x's, so different x's. So in fact, you can actually set up models where the marginal distributions of these x's are not normal. There is a very famous model used in the CDO world, this model of David Lee that Paul mentioned with the Gauss copula. And in this model, in fact, David Lee has critical variables which are effectively exponential distributions from survival analysis. But because he uses the Gaussian copula to put them together, the net effect is that it's equivalent to a Merton-style model. So this seems a little bit abstract, but in the literature there are some different models, but as soon as you decide to use the Gaussian copula, you get the same thing.
The philosophy of maybe of the whole section,
Yeah.
the whole chapter is a little bit the following. You would put yourself into the shoes of, say, as chief risk officer, chief credit risk officer at a bank. You have a huge loan portfolio.
Each of turn around to the audience.
Yeah, I can try. Each of them has, each of these loans has a default probability. Now, this chief risk officer has to trust the default probabilities that are given to him by either his scoring system or by his front office people. What he or his team are worrying about is, given the default probabilities of the individual firms, how does sort of the joint distribution of these defaults affect the loss distribution. So the viewpoint we're taking all the time. Here the idea is also the following, okay, he may then use such a latent variable model to join these individual default probabilities into a joint model. The individual default probabilities, that is the probabilities of going over the thresholds are given, but how does the copula of these latent variables he uses to create the joint model affect the outcome of the analysis? That's sort of the question that Alex is asking.
Yeah.
And that's the point of view you will take most of the time. Individual default probabilities, right or wrong, are given to us, and we want to understand the joint model. And so we know the margins, we're looking into the joint distribution. It's very much the same philosophy as the one with the copula model we get. Okay. The other bit is also important, but then it would have to be important credit scoring or something like that, which is a little bit withdrawn from what you did there. So the philosophy is really the same.
But now I'm actually going to put the copulas aside. They're in there implicitly in these, I've called, so Rüdiger used another name for them, which sometimes they're called latent variable models. In the book we call them threshold models. The copulas are implicitly in there, and in fact, if you want to write down formulas for the probability that 2 firms default, or 3 firms default, or k firms default, these formulas involve copulas, which is quite nice. So lots of things can be calculated in terms of copulas. So the copulas are in there, and but the word copula now will disappear. And as I've said, in fact, for our purposes, we will stay with a model that actually has a Gaussian copula, because that is the natural consequence of doing a multivariate Merton. So all that this slide does is effectively rewrites Merton in a situation where you have correlated geometric Brownian motions. So for every firm, you have an asset value process, and each one may have a different drift, each one may have a different volatility, each follows an SDE of this kind, but correlation enters through these Brownian motion driving terms. We're not going to go into stochastic calculus and all that, but these are correlated Brownian motions, so here enter the correlations. And if we now look at what is the value of the assets at the time horizon t, when debt has to be repaid, then it's going to be multivariate log normal. It's going to be multivariate log normal because this vector here will be multivariate normal. And in fact, the correlation matrix will be given by these rows here. So this will be multivariate normal, this will be multivariate log normal. But that doesn't really matter because whether it's normal or log normal, because in terms of the picture that you saw, we can just turn a log normal threshold model into a normal threshold model by taking the log of the asset values and by taking the log of the threshold. In its basic form, Merton is a default-only model. Merton was only worried about these contingent claims. Is there default? Isn't there default? But of course, you can extend it to have multiple thresholds which may determine rating state migrations.
So what you call V now is what you called X in the slide before?
Exactly. What I called X in the general models, this is the general model. Very good, Frank. Yeah. Yeah. What I called X before in this particular example is V or log V or log V. Doesn't matter. Yeah. 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 Or log V. Well, here it is. Here it is. X and yeah. So in this model, in fact, let's say B is this vector of liability levels that have to be repaid. And so the threshold representation, instead of XD, we'd have VB. So instead of XD, we'd have VB, but we can do some standardization. We can, as I've said, we can go from asset values to log asset values, and we can subtract mean terms and divide by standard deviations, and we can go from this basic model, or this version of the model, to something which is entirely equivalent, where the X's are standard normal. So by the action of standardization, we can go to X's which are standard normal, and where the dependencies now only come, where the dependencies come through this correlation matrix rho, or P. And of course, this random vector has the Gauss copula, as we learned this week. So in practice, rather than working with the model VTB, which is what immediately comes out of Merton, it is actually usual to start simply with a model XD, where X is standard normal, but they're correlated, and the Ds are the thresholds which will give you default, or we can add further thresholds if we're interested in migrations. So, now to come to the question of calibration, or is it estimation? I have to think which one it is here. There are two practical challenges. If we want to set up a threshold model, we would have to determine D. We would have to determine D, the default threshold, and we would have to determine the correlation matrix, rho or P. Those are our two challenges, but we may have a lending portfolio of 10,000 firms, maybe more. So this correlation matrix may be a D, it's a D by D matrix, and D may be very large. And so we would probably want to calibrate the correlations in a relatively parsimonious way, because in fact, we don't know a lot about the correlations between any two firms. It's very difficult to put a different correlation number on every pair in our portfolio of 10,000 firms. I said D, of course. In fact, the notation we use, especially in this chapter, D becomes M. Small m is the portfolio size. So in its most general form, there are that many parameters, typically large. So how do we reduce dimension? Well, this is why we did the factor model this week. We used it with the bond portfolios. We use it here again, which is your question. How do we describe these dependencies that come from common economic factors? Well, we're going to use very standard, the standard models that are used in industry where the factors have a industry and country interpretation. The major vendors of credit risk models, so I'm thinking of the credit metrics solution, for example, which was created by the risk metrics group and then company. They use a factor model of this kind. The KMV modeling philosophy, I mentioned yesterday that Kielhofer, McQuown, and Vazicek had turned the Merton's model into a company called KMV, where they measured default risk through basically using Merton's machinery to estimate a distance to default. Now, they also have to describe the dependencies in a portfolio, and they also use country and industry effects. That model still exists. It's now belongs to Moody's empire, Moody's Analytics, and they call it the public firm EDF methodology. And to model the correlations, they have a huge factor model, which they call GCOR, global correlation. But really, it's the same philosophy as that we've tried to explain this week. What else do we need here? Okay, so the factor models, how are they going to work? So this is actually revision, but we've used a slightly different notation here in this chapter. Every firm has a critical variable, xi, and in a factor model, you divide it into a systematic part and an idiosyncratic part. So the first term is the systematic part. Every firm will have a systematic component fi tilde. Beta I here will be a weight between 0 and 1, and this is the idiosyncratic part. So the larger beta I is, the more systematic the firm is, the more it is influenced by the larger economy. The smaller beta I is the more idiosyncratic. I have a feeling the batteries are starting to peter out. I'll keep going like this. Okay. So this number beta I between 0 and 1, we'll estimate some of these later on, at least that's my intention, by 10 o'clock, to actually estimate some beta I's and to go back to some of the data I looked at. Okay, let's take a 1 minute time out, actually. How's that? Okay, so beta I measures the amount of systematic risk. So the part of the variance of xi, which is explained by the common factors. Now, fi tilde, we will assume that fi tilde is a weighted combination of these common factors f. The common factors f, and these factors will have country and industry interpretations. It's written down in a slightly different way to Chapter 6, but it completely falls into the framework of Chapter 6. So the factors themselves, we will standardize them so that they are mean 0 and variance 1, but they could be correlated with a correlation matrix omega. So we'll come back to this model at the end, but suffice it to say at this point that the Fs have this country and industry interpretation, and we're going to have to calibrate a factor model to reduce the dimension of the correlation matrix. There are some calculations here which are not too important, actually calculating asset correlations within this model, and then counting the number of parameters you would have typically in a factor model, how you would reduce the number of parameters from m times n minus 1 over 2 to something substantially smaller. But I think we can skip those calculations and move on. Now at this point, we move to another way of presenting a credit risk model, and we start again with what is an abstract definition. And this, to begin with, this looks like something that is completely different. But in fact, it's going to be the same as what we've had before. But we're going to look at credit risk through different eyes. We are going to write down a very simple one-period reduced form model that we call a Bernoulli mixture model. So in a Bernoulli mixture model, all we're going to assume, we're not going to think about Merton interpretations now. We're going to think simply, abstractly, that there is some set of common factors, and they're going to have an economic interpretation. But here's the critical point. Given a realization of the factors, defaults are going to be conditionally independent. Now, the simplest kind of dependence model that you can build is a conditional independence model. That's the simplest thing to do. We believe that default risks are profoundly dependent. We've seen that this is important. We have good economic reasons for expecting dependencies. The simplest way we can model dependence is through conditional independence. That is, by assuming that conditional on some variables, we have independence. It's simple because it's relatively tractable, as I will try to show. You may if you want. Yeah. Okay, so these are called Bernoulli mixture models because we're still interested in default and non-default. We could have multinomial mixture models if we're interested in different rating transitions, upgrades and downgrades, but certainly in this chapter we'll just think of the 0-1 case, although we could extend it to the multinomial case. So this is the abstract definition of a Bernoulli mixture model, but the idea is really simple. P is going to be the number of factors we have to condition on. And in this model, we'll call the factors psi. So psi here is a vector of dimension P. P could be 1. The one-factor model in credit risk is really popular since Vazicek's work. So P could be 1, or it could be 9 industry factors. That's the example I will do later on. And then the default indicators, they are said to follow a Bernoulli mixture model with factor vector psi if they are conditionally independent given psi, which means we can find some functions, pi, and conditional on psi, the components of y are independent, and the conditional default probabilities depend on psi. So you're going to see here big psi's and small psi's. This may, well, look here. This may be confusing. Big psi is a random vector. It's the usual convention. Small psi is a particular set of realized values for economics. So again, think of these factors as having industry interpretations. Now, why did I say that a conditional independence model is an easy model? Well, it's always easy to write down expressions under independence. And for example, suppose we're interested in a particular pattern of defaults and non-defaults. So we're interested in the probability that company 1 defaults and company 2 defaults and companies 3, 4, 5, and 6 don't default. Well, if we condition on the factors, we get a product form. Don't worry too much about the details. Just notice that if we condition on the factors, we have a product form because of conditional independence. But when we integrate out the effect of the factors, or rather, we have to then integrate out the effect of the factors to get the unconditional distribution of defaults. So we have a p-dimensional integral over the distribution of these abstract factors. And if p is 1, this is a one-dimensional integral. If p is 3, this is three-dimensional. And this may not be too hard to do, particularly if p is 1. This is going to be easy to do numerically. And even if p is a bit bigger, this will not be too difficult. So computing these things may not be too difficult. The default probabilities themselves will be given by the expected values of the conditional default probabilities given the factors. Now, what are we ultimately interested in? We're ultimately interested in the portfolio loss, L. So actually, in any kind of model, we would like to determine the loss distribution. We would like to determine FL, the loss distribution. Doing that directly is not so easy. Computing a convolution, because of course this is a sum of random variables, so computing the distribution of a convolution, particularly when the terms are dependent, is not so easy. But what is incredibly nice in these models is that we can compute either characteristic functions or Laplace transforms really simply. And I want to show you an R script now, which will just give you a sense of why this is a nice thing to be able to do. I've written down the Laplace transform of this model here. And what you see again is that the Laplace transform involves an expression we can evaluate and an integral over the distribution of the factors. And this integral will be a low-dimensional integral. So we can do this. Let's just say that we can evaluate this. It's difficult to evaluate that directly, but we can evaluate the Laplace transform. And we have these methods, Fourier inversion methods, that allow us to go from Laplace transforms to distributions, or to go from characteristic functions, which are related to Laplace transforms, to distributions. And I'm going to give you a little example now, which I think is useful. We'll see what you think. And to make it simple, in fact, I will switch off the factors. I'll just make it an independence model. So this is, if you want to see where this is in chapter 11. There are some scripts in chapter 11, but there's a little script here called FFT for CF. FFT for CF. And it starts with coding a Laplace transform. And this Laplace transform is the Laplace transform. If you went through the code, you would see that it is in fact this expression here, but in the case where there is no expectation, because I won't have factors, just for simplicity, so I don't have to do a numerical integral, which I could do. I won't have factors, and so we will have independence rather than conditional independence.
FFT is fast Fourier transform.
Yeah, FFT is going to be fast Fourier transform. So this function is going to compute the Laplace transform of a credit model, and here's the data that goes into the model. I have 20 firms, okay? I have 20 firms, and here are my exposures. I lend the first firm £5, 500,000 Swiss francs with 5 somethings, and the second, third, fourth, and I lend the fifth, sixth, seventh, and eighth firms 10,000 Swiss francs, then 20, then 30, then 40. So I have different exposures. And now I have some probabilities of default. The first 10 firms are going to have a 10% probability of default, and the second 10 firms are going to have a 5% probability of default. So if I just put this information together, you'll see what I've got from my portfolio. Okay, so here's the 20 companies. So the first ones I lend 5 million. It's a million now. And the probability of default is 0.1. Then I lend 10 million, 0.1, but you get down here. So I'm starting to lend some firms 20 million, and the default probability is 0.05. Now, simply to compute, so what's the portfolio loss? Well, we have the sum of the exposures times the Bernoulli indicators, and these Bernoulli indicators have different probabilities. Well, there are only 2 values, but we could do anything we like. I could assume conditional independence, but just for simplicity here, we'll just take them as independent. But even computing the distribution function of the loss is actually quite difficult because everything's different. We'll try it step by step in a second. But I'm going to show you a piece of, I still think it's mathematical magic. But what I'm going to do, forget about the first two codes, is I'm going to compute the characteristic function. Now, the characteristic function, you get it from the Laplace transform. So I'm going to take the Laplace transform of my little credit risk model, independent defaults, and what I have to do is evaluate it at an imaginary number to get the characteristic function. This 1i here is the imaginary number. And I put in my probability of defaults and exposures. And
Why do you add 1 to exposure?
why do I? Oh, why, this one here.
No.
Oh, because doesn't really matter too much. Yeah, so the total, the maximum possible loss that I actually could make would be the sum of all these exposures. That would be the maximum possible loss I could make, would be the sum of all these exposures. So I'm actually going to consider the total loss. Plus 1, I'm also going to consider the scenario where there's a 0 loss. We won't worry about those details. Instead, have you ever seen a characteristic function?
The n is the number of different values the loss can take.
Yeah, the number of different values the loss can take is n. Yeah, the number of different values the loss can take is n. It's not quite true because some are impossible. You can't lose 4. Yeah. Some are impossible. Yeah. That's my credit risk model. That is a coding of my credit risk model. These are real numbers. These are imaginary numbers. And this is my credit risk model.
By the way, this is the slide that Alex made yesterday after 2 bottles of wine.
Yeah. So.
No, this is how to walk.
Yeah. Yeah.
That is the phrase you made when you walked.
Yeah. So, but that codes this model. This in the complex plane. This is a coding of the model, and so what's the FFT now? As Paul said, it's the fast Fourier transform. So if I apply the fast Fourier transform to this characteristic function, I'm going to get the loss distribution, and I'm going to plot it. And so this is what. So I apply the fast Fourier transform. What I've effectively now computed is I've computed the density or the probability mass function. It will add up to n. This is actually n. And so I will have to standardize by dividing by n. And then I get the probability distribution. So this is the actual probability distribution. That is the probability I lose nothing. I can't lose 1, 2, 3, or 4. I could lose 5 million if one of my guys defaults that I've lent, and I lent 4 of them 5 million. So there are some ways of losing 5 million. There are some ways of losing 10 million. I could lose 2 5s, or I could lose 1 10. So there's some ways of losing 10 million. And all of these probabilities will be correct. All of these will be correct. So how many ways of losing... what's the probability of a loss of nothing? Well, everyone has to survive. The default probabilities are 0.1 and 0.05. So basically, if I compute 0.9 to the 10 times 0.95 to the 10, that will be that value. So I'm just checking that this makes sense. That's what it should be, and that's what it is after the magic of the fast Fourier transform. How do I lose 5 million? Well, I have to lose one of the guys that I've lent 5 to, and there are 4 guys. So basically, I have 4 times a default probability of 0.1 times a survival probability to the power 9, and all the other guys, they have to survive. So I can, by combinatorics, I can work out what it is, but it starts to get, you can see it starts to get confusing. So you have to keep your wits about you. That's the probability of losing 5 million, and that's exactly what is computed by this technique, and so on. How do I lose 10 million? Well, then it gets more complicated. To lose 10 million, I could lose one of the guys I lent 10 million to. or I could lose, that would be here, and I could lose 2 of the guys that I lent 5 million to. So you do the combinatorics. Anyway, it works. So I've always liked that example just to say, because if I just showed you the Laplace transform and I say this is useful, you might not believe me unless you've used these techniques, which of course, if you're non-life insurance actuaries, you might have done. But if I can compute this, it is useful. And the point is, in a Bernoulli mixture model, I can compute this because this is a low-dimensional integral, maybe dimension 1 or dimension 2. Okay, so when I say this is useful, I hope just with this very simplistic experiment to have convinced you that it's useful to have models where you can compute these things. It also plays a role in importance sampling. Another way that we could determine the loss distribution in one of these credit risk models is by Monte Carlo. We could take our model and we could start simulating defaults. We could simulate the factors, and then conditional on the factors, we could simulate the defaults. If we just did that naively, it would take a while because default is a rare event. And so we'd be simulating for quite a long time, but it would work with modern computing power. But we could really accelerate the Monte Carlo by doing importance sampling. That is, we could bias the sampling so that we were increasing default probabilities, for example, so that we, in a smaller number of simulations, we could get accurate results for the loss distribution. So in chapter 11 of the book, you can learn a bit about these techniques for portfolio credit risk models. But the important thing is to have a model structure that allows you to do these things, and the Bernoulli mixture model is such an example. Okay. Now, it looks like we've got 2 different kinds of models. We've got Merton's threshold models on one hand, and suddenly we've got these Bernoulli mixture models on the other hand. But in fact, often they're the same thing. And there's now a pretty classic calculation that people do to go from a Merton-style model to a Bernoulli mixture model. So this little section here, taken from the textbook, shows how a threshold model is also a Bernoulli mixture model. In fact, all of our model examples in the chapter would have this Bernoulli mixture representation. So I think I've said this. Although the mixture models seem at first glance to be different, it's important to realize that the majority of useful threshold models, including Merton, can be represented as Bernoulli mixture models. So there's sort of a 2-slide calculation here, beg your pardon. There's a 2-slide calculation. In our threshold model, default occurs if xi lies below a critical threshold. And we are saying that we're going to model xi through a linear factor model where we have systematic factors and idiosyncratic errors. And the point is that if we identify these factors f here, if we identify them with the psi's in the Bernoulli mixture model, then we can represent it as a Bernoulli mixture model. So I've recapitulated the assumptions of a factor model, normally distributed factors, beta i's between 0 and 1, errors which are independent, or IID, and moreover independent of f. And under these factor model assumptions, we identify psi with f. It's perhaps slightly better to identify psi with minus f. It's just a detail. And then you do a little calculation where if we identify psi with minus f, because these are independent, that's where the conditional independence comes from. Defaults become conditionally independent because these epsilons are conditionally independent, and we can compute the conditional probabilities of default. I have my eye on the time here. Maybe we can just do this. So, if psi are the factors, the conditional probability of default, what is it? It's the probability that obligor I defaults given psi, or given f. So it's the probability that the critical variable is below the critical threshold, given psi or given f. So let's go over to the f. The probability that the critical variable is less than the critical threshold, given f takes some set of numbers, take some set of values. You then insert the factor model. So you then insert this. You take this and you put it in here, and you shift the systematic part to the right-hand side, because if we're conditioning on F, you can take this as a fixed part, and you can shift it to the right-hand side. And then you have a probability which is essentially normal, because epsilon is normal. So the normal CDF comes in. Yeah, we're using the, and epsilon I is independent of F. And so using that, we have the normal probability, and we get an expression like this. The final thing we can do is we can acknowledge that the threshold DI in the Merton model, it will be given by phi inverse PI. PI is the unconditional default probability. So PI is the probability of being below the threshold, and if the critical variable is normal, then we have to put the threshold DI at phi inverse PI. So you get a formula here, and if you've read the credit risk literature before, you've probably seen this formula derived in the one-factor case by Vazicek. People call it the Vazicek formula, so particularly when there's a single factor here, they call it the Vazicek formula, and it gives you the conditional probabilities of default in a Bernoulli mixture representation of a multivariate Merton model. And so using this, I could, for example, apply my fast Fourier transform methodology to compute loss distributions, or I could do importance sampling. I'd also need that expression for the characteristic function to do the importance sampling, or the Laplace transform. So this is a useful insight. What I'm trying to say is this is a useful insight. It is a useful insight to see that Merton's model with the factor structure for the critical variables turns into a Bernoulli mixture, because that eases computation. It eases simulation. Conditional independence is easy to simulate, and it eases calculation because I have low-dimensional integrals over the factors. In a one-factor model, it's a one-dimensional integral. For the actuaries who are here, who's familiar with the idea of gamma Poisson mixtures in non-life insurance? And I won't ask you to say anything. Who's familiar with the idea of gamma Poisson mixtures? Actually, so quite a few hands. It's the same kind of thing. We're doing Bernoulli mixtures, but these are rare events. Default is a relatively rare event. Certainly for the higher rating categories, it's a rare event. We know that the Poisson distribution is the classic distribution for rare events, and that we can approximate Bernoullis or binomials with Poissons if the event probability is small. So actuaries have made a valuable contribution to portfolio credit risk modeling. And the model that is known as credit risk plus, actually I'd forgotten it has Swiss provenance. Paul may know the story, but it comes out of Credit Suisse, and it was built by actuaries because actuaries knew about gamma Poisson mixtures. Wouldn't it be nice if I could do this expectation analytically, if I didn't have to do a numerical integral? Generally, for the Bernoulli mixtures, I would have to numerically do the integration to get the expectation. But if I change to Poisson, I can get a model that is much more tractable, where I can do everything analytically. And so that's quite nice. And that's what was recognized by some actuaries. So let's see, what's important here? Because default is a rare event, we can actually approximate the Bernoullis with Poisson. And if we instead of taking normally distributed factors, if we were to take gamma distributed economic factors, we would get a very, very tractable model. And this was the insight of the actuaries who were working for Credit Suisse. Don't know who they were, but you may. This is going back 2 decades now. 1997, and they proposed a model that's still around and has been well studied called credit risk plus. And in this model, we replace the Bernoulli default indicators by Poisson variables. That seems a little bit strange at first because a Poisson isn't 0 or 1. A Poisson is 0, 1, or 2. And so what that means is in the model, you sort of admit the possibility that a company defaults more than once. It can default 0 times, 1 time, 2 times, 3 times. But because of the parameter values, the probability of more than one default tends to be very, very small. And of course, firms can default more than once. They can default, their debt can be restructured, and then they can default again. So, but anyway, you replace the Bernoullis by Poissons, and the factors, they no longer have normal distributions, they have gamma distributions. And you get a very tractable model. I'm not going to go through the mathematics of that. There are a couple of slides on that. I thought for actuaries, because this is a summer school for the Swiss Association of Actuaries, that I wanted to pay credit to actuarial thinking in credit risk, and to mention this model, credit risk plus. What sort of things do you get? You get that in this model, the distribution of the number of defaults, if you make this Poisson and gamma assumption, or conditional Poisson, conditional gamma assumption, you get negative binomial distributions. That's what you knew, right? That if you take a gamma mixture of a Poisson, you get the negative binomial distribution.
So you get clustering.
Yeah. Yes, you get a model where the variance can be higher than the expected value, which is quite popular in non-life insurance. So we get a model where the number of defaults is, if there's one factor, it's negative binomial. If there are p factors, in general, the number of defaults is a sum of independent negative binomials. And then you get even more. Analyzing the loss itself, the Credit Suisse group, basically they discretized the losses. So they considered, for the actual losses given default, they considered, or the losses in the event of default, they did a discretization, which allowed them to get, and I'll just kind of jump to the final result here. It allowed them to get a model with compound negative binomial distributions. So credit risk plus, for the portfolio loss distribution, it gives you compound negative binomial distributions or sums of compound negative binomials, and they are pretty tractable. So if you're interested in that, try reading a section in the book, and there is quite a nice R script where we calibrate a credit risk plus model, and we compute this. We compute the Laplace transform of the credit risk plus model, and then we invert it to get the distribution of losses in credit risk plus.
So just, of course, one can make many historical stories about that, because if we were very close with Swiss also, there's one question for the audience. The essential point is these companies compound negative binomials, sums of negative binomials, and sums of negative binomials. And now exactly when you use fast Fourier transform, then you can calculate the probability distributions. What other method do you actually know, and is linked to a famous actuary to calculate some of these probabilities recursively? Tangent recursion.
Convolution.
That's it. It was rather interesting. We were discussing, it was mainly my colleague Freddy Delban, who said he was discussing what these people were doing with this credit risk plus model, and he said, he pointed at some of their calculations, and you realize you're sort of rediscovering, or you're really looking at tangent recursion. And I think this is one of the very nice examples. I think, as Alex also stressed, how actuarial thinking in this kind of world is extremely useful. Tangent recursion was also there. Just a story.
Yeah. So that's nice. There are actuarial contributions to credit risk, and credit risk plus remains a really nice portfolio model where you can do lots of nice calculations and get the loss distribution. So the final topic was just to give a little bit more insight into the estimation stroke calibration, because for a long time when Rüdiger and I studied these models, we read these model descriptions, but and we talked about these factor models, but it was a little bit unsatisfactory because we never actually tried to calibrate one. So we've tried to calibrate one just to give a sense of how it works. So let's go back to Merton, to multivariate Merton, that is to the threshold model where the critical variables are multivariate normal. You can also call it the Gaussian Copula model. So we go back to the Gaussian Copula model. There is a vector of critical variables x, which is multivariate normal, standard margins, correlation matrix P or rho, and some thresholds D. So what do we need to determine? We need to determine D, and we need to determine rho. That's all we have. We need to get D, and we need to get rho. In industry, those problems are generally separated. So you don't estimate it all at once. You separate the calibration of the vector D from the calibration of the factor model X. I've never been completely strict about differentiating calibration and estimation. I tend to think of estimation as a subset of calibration, being a vaguer word in the English language, which just means getting parameters somewhere. And estimation is a more precise set of methods. So we've got to get the parameters somewhere. We've got to calibrate. So just really quickly, how do you get the Ds? Well, you get the Ds from the Ps. You get the right thresholds by getting estimates of default probability. Where do you get an estimate of default probability? Well, you have some choices. You can use ratings. You can go to Moody's and Standard & Poor's and map the ratings to default probabilities using their data. If it's retail customers, then you probably have to use your scorecards. You can use the methodology of KMV, essentially, which is to use prices to infer distances to default and therefore probabilities of default. We haven't really gone into this methodology, but it's a big topic in Chapter 11. But there's a methodology where you use prices. So we'll assume that this bit is doable. And so we will concentrate on how we get rho, the correlation matrix. And okay, so I've mentioned this bit here. And I just rewrite the factor model once again. This is the factor model we use. We have the Fi tilde is a linear combination of industry country factors. So the factors typically represent country and industry effects. In all the portfolio models I know, that's precisely what they represent, country and industry effects. There are some little constraints on everything, the way we've set it up. We've set it up in such a way that this is N01. This is mean zero and variance 1. And we set it up, and so that imposes some constraints, so that the variance is 1. The variance of this part will be beta I. The variance of Fi tilde is constrained to be 1. And the variance of this, and the epsilons are standard normal, so the variance of this part will be 1 minus beta I. So this constraint that the systematic factor has unit variance, it implies some conditions that have to be respected for the covariance matrix of the factors. Okay. Different industry models use different data to get the correlation matrix. There's a nice document that you can probably find on the internet. We have copies of it from Moody's, where they describe their GCOR, Global Correlation Model. And in fact, they have ways of getting correlations for different kinds of obligor, whether that's big public corporate firms, or whether that's SMEs and retail customers or even countries. What I will do is the public corporates. So we'll actually we'll go back quickly to the Standard & Poor's data in the last 5 minutes. The submodel for public firms is calibrated using weekly asset value returns in GCOR. Now, we can't do that because I can't do that because I have no data on asset value returns. I have data on equity returns, and the only people that have data on asset value returns are Moody's, because they have the methodology that reverse engineers asset values from equities. Yeah, that's this KMV methodology. It's called the Moody's Public Firm EDF model. And so you never observe asset value time series ordinarily, because the entire assets of firms are not traded on markets, just part of the assets. So we will do what credit metrics does, and credit metrics looks at weekly equity returns and views these as a proxy for asset returns. If you believe in Merton, what you really want are asset values or changes in asset values. Doesn't really matter. Asset values or changes in asset values, but as a proxy, we take weekly equity returns. And so I'll just go quickly through a kind of generic procedure for estimating the factor model. I don't have country factors because I'm just going to take the American data, but I have industry factors. Okay, so yeah, so I've got a high-dimensional multivariate time series. In fact, I've got 365 stocks that if you remember back to Tuesday, I think, 365 stocks. So that's my high dimension. I have weekly stock returns.
Briefly after the break, I think it's important.
I'm worried we run into time trouble. What do you think, Rudiger?
I think it would be good to do it, because it brings together a lot of
make
things.
a break now, you just do it. You've been trying to rush through the whole
That would be a
chapter
pity, I
anyhow,
think.
so-
Yeah. Okay, well,
And I have to cut short of some other things.
yeah. Okay. It's going to take me about 5-10 minutes to do, and it seems to make sense to just do the model after the break. So,
I think so.
so let's have coffee. Yeah. Okay, I actually don't have very much at all that I still wanted to do. And so I'll take hopefully not too much longer than 5 minutes just to bring my story to a conclusion. I just wanted to go back to the idea of actually estimating factor models, because in fact we've done most of the work. If we are lending to the 367 companies in the Standard & Poor's index that I analyzed the other day, if that's our portfolio, what we have to do is estimate a correlation matrix based on an industry factor model for those 365 companies. And so all of the parameters I need are, what do I need to determine? These factors are industry factors. I'm going to need their covariance matrix, or rather their correlation matrix, because I standardize them to be mean zero variance one. So I'm going to need the correlation matrix omega, and I'm going to need for every firm a beta I. And so we'll just get those numbers from Standard & Poor's and have a look at them. I have written down the procedure as a series of steps. What's important here, I'll just recap on the data. The data that are going into this are obviously equity returns. Ideally, it would be asset value returns because of the methodology of Merton, but I will do it with equity returns. And it is a fundamental factor model. Of the three kinds of factor model, it belongs in the fundamental category. So essentially, I can just use the analysis from Tuesday and collect the numbers and finish. I don't think we need to go through step one. This actually explains the method more generally. If we had country factors, if we had industry factors, I even consider the case where you assign a company maybe not 100% to one industry, but you assign it 60% to one industry and 40% to another industry, or 80% to Europe and 20% to the Far East or something. So you could have more general models, but the one that I fit is the easiest kind of model, where every company is uniquely identified with one industry. So we won't go through all the steps in one, but I just wanted to say that once again, it's a fundamental factor model because I have my data on X, I have weekly equity returns, I know what kind of structure I want, I have identified each company with an industry sector, and so what I need to do is reconstruct the factors, and from the factors I'm going to get the correlation matrix, and then the final thing I'm going to need is a beta for every company, which will measure how systematic those companies are. So it's a fundamental factor model, and we do least squares. So this was the estimator we actually used on Tuesday, a least squares estimator. On Tuesday, the A was a B, but that doesn't really matter. And we can refine the estimates by using generalized least squares. They should be slightly superior, more efficient. And so I will just run those estimators, and we get the factors. And they're here. The factors are here. So I had 9 sectors. You probably remember this picture. All the companies have been identified with one of these: consumer discretionary, energy, financials, materials, etc. So the script that is called credit factor models is in fact more or less identical to the script that you saw on Tuesday in chapter 6. It more or less repeats that script. One little detail is when I estimate the coefficients, I standardize them to make sure they are mean 0, variance 1. So I've just executed line 101. I've plotted the zoo, the ordered object, and you're looking at this, but these are time series which have been standardized so that they are mean 0, variance 1. And this is the covariance matrix here. So what you see here is the covariance matrix, which is also the correlation matrix because they're standardized. So this is omega. So I have omega, the correlation matrix of the factors. And the only thing I still need are the beta i's. So we're going to construct the systematic terms for each obligor. Going back to the notes, what I have are the factors ft at each time point. That's the 9 time series. I know which firms are in which sectors, so I construct the systematic part for each firm, FTI. I just construct that. And then the next thing I'm going to have to do is I'm going to have to get the beta I. And one simple way of getting the beta I is to regress, do time series regression of the asset return, or rather the asset return, the equity returns on those systematic terms, and that will give me the beta i's. So you can sort of map it to what I've done. A is the matrix A in the slides. F tilde, this operation here, has constructed the systematic part for every obligor. These systematic parts will have mean 0 and variance 1. So you can see the names of the 367 stocks. This is just checking that indeed they have variance 1. And then finally, by regression, I will estimate the betas for every one, and we will plot some of them. So let us look firstly at these companies. So there's 15 companies. These happen to be the ones with the highest betas. You can see that these points are pretty well aligned on the regression lines. They're not going to be perfect, but these are very systematic companies. They have high betas, beta i's. So in fact, their returns are extremely well explained by the industry returns, by the sector returns. And then at the bottom of the list, I'll just show you the pictures for the smallest betas. So these are the pictures for the smallest betas. Slightly less impressive regression. So those are the ones that are more idiosyncratic. They are not quite so well explained by their industries. And so there's something more idiosyncratic going on with these titles. But the slopes of these lines are beta I, and I now have all the information to fix the correlation matrix. I have the correlations of the factors themselves, and I have for every firm a beta I, and so the model is calibrated. I've calibrated my model, And the last step was really important because another thing you should take away, the accurate estimation of beta in the last step is particularly important because this will affect the tail behavior. It goes back to the very first picture. The more that these firms... the tail behavior of the portfolio credit loss. The more that these firms are affected by common factors, the more that will contribute to the tail of the credit loss distribution. Okay. So you just, I hope, get a sense that it's possible, even with toy examples and with R. And now we'll just switch over the projector.